Okay, welcome back. So today we are going to go over the practice for 1.7a. So let's just dive right into this. So I am assuming that you've already watched the 1.7a video from the algebras. So now we're going to go through the practice. So looking at number 1 here, we want to find the domain of the following rational functions, and we want to use interval notation. So to find the domain of the rational functions, we have to find where the denominator of each of these functions is equal to 0. So we can't let the denominator be equal to 0, because if we let it equal to 0, then we're dividing by 0, and we can't do that. So we have to exclude it from our domain. So we can solve 2x plus 5. We don't want this to be equal to 0. And so, if we solve this, we'll just move 5 to the other side. We have 2x can't be equal to negative 5. And then dividing by 2 on both sides, we have x cannot be equal to negative 5 divided by 2. So, that means that this value cannot be part of our domain. And so when we're writing it, using our interval notation, we write this from negative infinity all the way to negative 5 over 2. And we put a parentheses because we're not including 5 over 2. And then we're going to do a union, so it's like we're jumping over that 5 over 2 onto the other side of it. And then from negative 5 over 2 to positive infinity. So visually what this looks like is it's like we have a number line, and our function is defined on its domain for everywhere except negative 5 over 2. So I could put a line here, and we have an open circle on negative 5 over 2. And everywhere else is fine. We have domain over there, we have domain over here. And all the way from negative infinity to positive infinity is fine, except for negative 5 over 2. And that's why when we write this in interval notation, it's negative infinity all the way up to negative 5 over 2, jump onto the other side of it, and then negative 5 over 2 to positive infinity. So let's try this next one. Again, if we want to find the domain of this rational function, we can't let the denominator be equal to 0 because we don't want to divide by 0. So fortunately, we can treat this with our zero product property. We have n plus 3 can't be equal to 0, or n minus 7 can't be equal to 0. We solve both of these equations simultaneously, and we have n can't be equal to negative 3, or n can't be equal to positive 7. So, if we were to put this also on a number line, goes from negative infinity to positive infinity. We have two values this time. It can't be equal to negative 3, and n can't be equal to positive 7. So we have open circles right there. Now any other value for x is perfectly fine. We have our function defined over here, our function is defined over here, and our function is defined over here. Just anything but negative 3 or 7. So when we're writing our domain in interval notation, we have from negative 3, we have from negative infinity to negative 3. Union, we jump over negative 3 onto the other side of it. So we start at negative 3 again, but just on the other side, comma 7. So we go up to 7 on this side, and then we have to jump over it, union from 7, and then off to positive infinity. So this would be our domain for this function. And yeah. Alright, and now this last function for 3. Again, we don't want our denominator to be equal to 0, or else it won't be defined, so it's not part of our domain. So we have to figure out where this can't be equal to 0. And it's basically like solving it for 0. We're just going to carry over this not equal symbol instead. And in order to solve this, we have to factor it. So we have to find two numbers that multiply to negative 15 and add up to positive 2. And so after you think about that for a moment, you'll arrive at the conclusion that, well, those two numbers would have to be positive 5 and negative 3. Positive 5 times negative 3 is equal to negative 15, and 5 plus negative 3, in other words, 5 minus 3, is equal to positive 2. So we know we have the right numbers here. So this cannot be equal to 0. And now it's pretty much like this problem over here, where this one was already factored. And so using our zero product property, you'll notice that as we've used this throughout the year so far, you basically can just flip these values here. If we have a minus 3 here, if we have a plus 3 here, this is going to be a minus 3. If this is a minus 7, it's going to be a plus 7. The only thing you have to be mindful of is that this only works if your coefficient in front of n or x or whatever variable is 1. So if these are 1s here, then you can just flip the values. Otherwise, you'll have to solve it like an actual equation like we did here for the zero product property. But that means we have x can't be equal to negative 5, and then x can't be equal to positive 3. We just flip our signs there. And now we got to piece together our domain. So if I make a number line so we know that negative 5 and positive 3 we can't have as part of our domain. Everything else is fine though. We can ignore the numerator for any of these functions when we're trying to find the domain. We don't care about what that is. But everything else is perfectly fine. We can plug in a number and we'll get a number out of it. So our domain, we go from negative infinity to negative 5. So negative infinity, negative 5. Jump over negative 5 onto the other side of it. So that's why we still have a negative 5 here. Go all the way up to 3. Jump over onto the other side of 3. So union 3. And then go on to positive infinity. And there we go. So we have the domain for each of these functions. Now let's go on to the next page. Now we want to find the domain of these rational functions, and we want to use interval notation still. So what we're going to do is, if we remember from the algebras, is that any time we saw for example over here, anytime we had a value that was not part of our domain, so like this negative 5 over 2 or these negative 3, 7, we had vertical asymptotes on each of those things. So our vertical asymptotes for a function tells us what our values could not be equal to. So right here, I'm going to use my red pen here so that we can see those asymptotes better. But where I've highlighted on our vertical asymptotes means that our function is not defined there. Everywhere else is fine. We can, if I plug in x is equal to negative 2 right here, that means that I have an x value of negative 2 and a y value of what looks to be somewhere around 3.5 or so. So our function is defined everywhere else. It's just these vertical asymptotes that it is not. So we just have to identify where those vertical asymptotes are, and that'll tell us our domain. So if we look at our graph, our function is not defined where x is equal to negative 1 and x is equal to positive 1. So this tells us x cannot be equal to negative 1, and this over here tells us that x cannot be equal to positive 1. And so when we piece together our domain, we have from negative infinity all the way up to negative 1. So everything over here is fine. But then we have to jump over our asymptote. And we go from negative 1 to positive 1. So everything in between these two asymptotes is fine as well. We have a domain defined. And then on the other side of positive 1, we have from 1 to positive infinity. And so this is our domain. Now, what about number 5? We have to look at our graph, and on your paper you'll be able to see it better, but there's a dotted line here, and that's telling us that we have a vertical asymptote there. And so, since we have a vertical asymptote there, we just need to identify what that value is. And if we look at that, it means that x cannot be equal to -2. And we don't have any other vertical asymptotes here. So, we can say that our function is defined, our domain is from -infinity all the way up to -2. And then we have to jump onto the other side of that from the other side of -2 all the way to positive infinity. So over here was fine, and over here was fine. We just have to skip over that -2, and that's why we use this notation here. And so this is our domain for number 5. Now what about number 6? We're trying to look at the end behavior. So the end behavior, this is always going to look like limit whatever your independent variable is called. In this case, we're just going to use x. As x goes to -infinity for f of x, and then limit as x goes to positive infinity of f of x. We're always going to start off, when we're talking about end behavior, as x goes to -infinity and x goes to positive infinity. And so I ordered them like this. So I put -infinity on the left and positive infinity on the right, just so, well, -infinity is over to the left and positive infinity is over to the right. And now we just have to look at what is the y value as x gets really far this way. So as x just keeps going in the negative direction, what is y doing? And when we were talking about polynomial end behavior in section 1.6, it was pretty common, or really for all of them, our polynomials either went to positive or negative infinity. But notice that this rational function, as we go towards negative infinity, it's not going up or down. I mean, it is increasing in the sense of that it's, as we go in the negative direction, it's increasing, but it's not going up, it's just flattening out. In fact, as we get really far out over here, it's still going to get flatter and flatter. It just, like, if I try to trace it, what I think it should be doing, it's just going to get flatter and flatter. And so we try to find, well, what is the y value that it's approaching as x goes towards negative infinity? And so if we try to approximate where that is, our y value looks like it's -4. And so we would say that as x goes towards negative infinity, f of x approaches, sorry, not -4, positive 4. So as x goes towards negative infinity, f of x goes towards positive 4. On the other hand, we have as x goes towards positive infinity, so now we're going to let x go towards positive infinity in this direction. As x goes towards positive infinity, we're tracing down here, and it just keeps going, but again, unlike our polynomials, this one just kind of flattens out like that. If we try to extend the graph, it's not growing really fast off into the towards positive infinity. It's not going towards negative infinity. It's not growing in either direction like this, where we would say, oh, this goes towards positive infinity, this one goes towards negative infinity. When it flattens out, it approaches some finite value. And in this case, it also is, if we just trace it out, positive 4 here. So the limit of f of x as x goes towards positive infinity is also positive 4. And so we ask, is there a horizontal asymptote? Well, if you notice, if you look in your paper, we still have this dotted line here. And most of the time when we look at graphs like this, you'll have this dotted line provided for you. It's there to help you. And this is a horizontal asymptote. We say yes. And what is the equation of that horizontal asymptote? Well, horizontal asymptotes, or just any horizontal line for that matter, is always in the form of y equals a number. And in this case, it's whatever the y-intercept is that's going to be that number. So in this case, it is 4. So instead of just y equals a, we actually have y is equal to 4. This is the equation for our horizontal asymptote. So what about number 7? Again, I'm just going to set this up. We have limit as x goes towards negative infinity for f of x. And then we have the limit as x goes towards positive infinity of f of x. Well, let's see. For negative infinity, as x goes this direction towards negative infinity, notice it's not tapering off to a single point. In fact, it just keeps going up and up and up, and it's never going to stop. Our graphs practically 100% of the time show us all of the important end behavior and important qualities of our graphs. So we can assume that as this arrow just keeps pointing up, the graph really does just keep going up further and further and further. So because it's not approaching any value, it just keeps going further up. F of x, the y value, just keeps going towards positive infinity. So we say that the limit of f of x as x goes towards negative infinity is positive infinity. And now what about the x value as we go towards positive infinity? Well, again, we can assume this function just keeps going further and further up. It doesn't stop. And so f of x, our y value, also just keeps going up towards positive infinity. So both of these have end behavior of positive infinity for both positive and negative infinity for x. And so is there a horizontal asymptote? No, there's not, because we don't have a, and you won't always have a dotted line, but especially if you see a dotted line, that's telling you that we have a horizontal asymptote. But our horizontal asymptotes are some value that our function approaches for the end behavior. And our end behavior, it's not approaching any flat line. If I try to draw one up here, well, our function, no, it doesn't approach that line. We have to keep going further. And no, it also doesn't approach that line. There's no line we could ever draw that it would, no flat line we could draw that would ever approach. So we say that we have no horizontal asymptote. And because the next question, write the equation of the asymptote. NA, not applicable, because we don't have one. And now what about number 8? So in behavior, we have limit x goes towards negative infinity, f of x, limit x goes towards positive infinity, f of x. And now we just want to see what is our function doing as we go further and further to the left. So as x keeps going this way towards negative infinity, what is the y value doing? Well, notice again here, this function, it starts tapering off. It gets flatter and flatter and flatter. And so we can kind of see that the value that it's approaching is going to be 0. The y value, it doesn't start increasing rapidly or decreasing rapidly, it just flattens out at 0. And what about the other side? Well, you see that if we extend that line, this function probably just gets really, well, it does, it gets really, really close to it, but it never actually gets there, but it goes also towards 0 as x goes towards positive infinity. So as x goes towards positive infinity, our y value, remember we're looking at the y value when we're evaluating this, the y value goes towards 0, right here. And is there a horizontal asymptote? Well, we've kind of already drawn it. It is this flat line here, yes, at y equals 0. And so this is our end behavior and asymptote for number 8. All right, let's look at number 9. So for number 9, this one I told students to skip, at least we skipped over it while we were in class just because, well, I wanted to cover it particularly in a video like this. So what we do is we need our calculators, and what we're going to do is we're going to go to y equals, and we're going to type in this function. 2 different ways you can type this in. If your calculator has this little symbol here, or let me use my red pen so you can see it against the calculator. If your calculator has this little symbol here, it looks like it's like a box divided by a box. If you hit alpha and then x, your calculator will make a fraction like this, and it'll be pretty easy to type in this function. However, not everyone's calculator does that, and so what you can do instead is you just have to be careful about typing stuff in. If you do x squared, so we have our x squared and then divided by, make sure you put everything in the denominator in parentheses. So I do x squared divided by open parentheses x squared minus 4x and then close parentheses. So now we have x squared divided by everything in here, which is going to be the same thing as what we have here. So now what we can do is we go to, if we just go to table, oop, I've already cleared that. Okay, so if I go to table set, usually what your table does is it'll look like this. It'll start off at like 0, and then you have to scroll to get to any particular value. And that's nice and all, but we're trying to go all the way to negative 10,000. We'd be scrolling for a very long time if we tried to get to negative 10,000 for x at this rate. It's never, well, it's not never going to get there, but you're going to be sitting there for a while. So what our calculator does instead is it also gives us the option to type in some value for x, and it'll evaluate it for us. So what we can do is we hit second and hit window, so it goes to table set. And if you scroll down to independent, so our x value, and if you scroll over and hit ask instead, so hit enter, and then you go to second graph, so table, now you can type in whatever value you want for x, and it'll give you a value for it. So if I type in negative 10,000 for x, it'll give me the y value when I hit enter. So the y value for x is equal to negative 10,000 is 0.9996. Okay. What if we type in negative 1,000? 0.996. What if we type in negative 100? We have 0.9615. What if we type in positive 100? We have 1.0417. If we type in 1,000, 1.004. And if we type in 10,000, we have 1.0004. And so, now with this information, we're trying to evaluate, well, is there a horizontal asymptote? And if we think about this, we're getting really big values of x in the negative direction, so negative 10,000, and the value isn't really growing. I mean, even at negative 100, we have 0.96. At negative 1,000, 10 times further down the x-axis, it only grew by 3/100ths. It's only 0.99. And then 10 times further than that, it's still only 0.999. It's not growing towards positive or negative infinity, it's approaching some value. And if it's not clear what value it's approaching, you can always type in bigger and bigger numbers. Like, what if I type in negative, let's see, that's 1,000, 10,000, that's negative 100,000. What if I type in negative 1 million? Now it's just saying 1. Now it's not actually 1. If I scroll over and highlight that 1, it gives me more decimal places. So in this column here, it only goes out to 4 decimal places, and then it rounds it. Over here, it's still not quite 1, but it's 0.99999, and then some other stuff. It's getting really close to 1 as x goes towards negative infinity. So we would say that the limit as x goes towards negative infinity for our function f of x, it's getting really close to 1. It approaches 1. And what about as we go in the positive x direction? So similar thing. What if I type in positive 1 million? So 1, 2, 3, 4, 5, 6 zeros for 1 million. And I also get a 1. If I highlight it, we have 1.00000 and then some other stuff. And if I keep on typing in a bigger and bigger number, it will get closer and closer to 1, never quite reaching it. We'll always have some left over here. But the limit as x goes towards positive infinity for our function f of x, it also approaches positive 1. And so, if we graph this, we can even see that, yeah, it kind of flattens out in both directions. And I could even graph our horizontal asymptote. We're going to take a guess that that's equal to y equals 1. And look at that. I think we can agree that our graph gets really close to y equals 1 without ever actually getting there. And we can zoom out. And even though those lines are practically right on top of one another because your calculator can't show with perfect accuracy, it only has so many pixels, but we can see that our function gets really close to that line, and you can trust that it never actually gets there, because if we zoom in, say, way over here, we have our function. And if we zoom in even further, in right there, so it looks like they're touching, but not quite. So they're always going to be some distance away from one another, but our function, the one in blue, will always get ever so closer as we go towards positive or negative infinity. So there is a horizontal asymptote at y equals 1. Well, sorry, that's addressing the wrong question. Yes, there is a horizontal asymptote, and it's at, and of course I write the wrong number, at y equals 1. Okay, now let's see if we can figure out what's going on with this function. So similar thing, we go to y equals, and we can clear out all of our stuff here. And we want to type in this function. So of course you can use alpha and then hit x and you can make a fraction. If your calculator doesn't have that, I'm going to type it in like that just so that everyone understands, because everyone's calculator will be able to do this. We'll type in x to the power of 3 minus 3x. I'm using x because our calculator doesn't interpret anything other than x. So we're just replacing t with x. So we put all of the numerator in parentheses and then divided by all of the denominator in parentheses. So we'll have 2x plus 1. So now that we have all that, we can go to second and table. And our table will already have these values in there. If we want to get rid of those values, we can just hit delete. So we have different values, so we got to delete those. But we can start over. And let's start with negative 5,000. So negative 5,000, what do we get for our y value? We get 1.25 E7. What does E7 mean? 1.25 E7. That means times 10 to the 7th power. So this is scientific notation, if you haven't seen this before. 1.25 E7. So what this really means is, if we quit out of this for a second, 1.25 times 10 to the 7th is actually a really big number. That is 12.5 million. So that's a big number. So don't be confused by that being a decimal there. This is definitely a very large number. If we go back to our table and we type in negative 500, it's not a decimal anymore. It is 125,124. So still a very large number, but not 12.5 million. What if we do negative 50? This is just 1,261.1. What if we do positive 50? 1,236.1. And then if we do 500, pretty large number, 124,874. And if we type in 5,000, we see 1.25 and then times 10 to the 7th, e to the 7th. You can write either one of those as long as you understand what that means. Again, this means, well, we already did that calculation because it's the same as this one for negative 5,000. That's 12.5 million, so very, very big number. And so we can keep on typing in bigger and bigger numbers, and notice that this one's a little over 1,000, this one's over 100,000, this one's over 12 million. The values just keep on getting bigger the bigger number we type in. What if I tried 500,000? That's e to the 11th. So this is getting even bigger. It's not even approaching a value, not a finite one. It just keeps on getting bigger and bigger. And so we say that with our end behavior, limit as x goes towards positive infinity, f of x, it just keeps getting bigger and bigger. We type in a bigger number for x, and it's going to give us an even bigger number for y. It goes towards positive infinity. And the same thing as we go towards negative infinity. Limit as x goes towards negative infinity of f of x. It doesn't slow down. A little over 1,000, over 100,000, over 12 million, and if we type in an even bigger number over here, it's just going to keep going. This will also approach positive infinity. So it doesn't have a horizontal asymptote. And because we don't have a horizontal asymptote, we don't have an equation for one, so it's not applicable. Now let's look at problem 11. We want to find h of 999. That just means what is the y value of our function h of t when we let t, our independent variable, equal 999. So when t is 999, what's the y value? It is negative 478. Now let's go on to b. The limit as t goes to positive infinity for our function. So as t goes towards positive infinity is going to be this direction. So as positive infinity, or as t approaches positive infinity, our numbers are not slowing down at all. They just keep getting bigger and bigger and bigger. And you can probably imagine we type in another number in for this even bigger. What if we do negative 99999999999? It's probably going to give us an even bigger number. So we say that that approaches positive infinity. Oh, sorry, negative infinity. Negatives. We have negative signs here. So really big number that is also negative, negative infinity. Alright, so as t increases without bound, the function, our h of t, we say approaches negative infinity. You can also say, and the way that I told you in class, is you say that it decreases without bound. So two different ways you can say this, and they both mean the same thing. Algebros, when I was looking at the answer key, they say approaches negative infinity. That's perfectly fine. And decreases without bound is also a very common way of saying this. In fact, they even say increases without bound over here, and they even say decreases without bound over here. So decreases without bound is perfectly acceptable. Now what about the y-intercept? So the y-intercept is, if we look at a function, if we have an x and y axis like this, and we have some function that's just doing its thing, the y-intercept we would say is right here, where it touches, our function touches the y-axis. So the coordinates for this function are given by an x value of 0. That's the only way it's going to touch the x-axis or the y-axis, is if it's on, or sorry, if x is equal to 0. And if we plug in 0 into our function, that'll give us the y-coordinate. So our y-intercept is given by 0, comma f of 0, or whatever our function is called. In this case, we have h of t, but wherever t is equal to 0, we plug that into our function, and we get a y value of 32. So the y-intercept, we can say is either y is equal to 32, or we can give the actual point of 0, comma 32. Personally, I would prefer us give the point like this, and I recommend you do the same. Now let's find out what is h of t doing as t goes towards negative infinity. So as t goes towards negative infinity, on our chart here, t is getting bigger and bigger in the x direction. So bigger and bigger negative number going into our function, and look at that. All of these are positive numbers, so it's going to be some positive something, but the numbers don't slow down. In fact, this is over 500,000, this is over 6 million, and then we have 7.3 times 10 to the 12. That means a really, really big number. That means we have to move this decimal place over 12 times. That's like 7.3 billion, I believe. And then 4.2 times 10 to the 32nd. I don't even know what that's called, but it's 4.2. Well, it's really 42 followed by 32 zeros. It's an absurdly large number. This function is not slowing down, it's just approaching positive infinity. So we say that this approaches positive infinity. Or we can say that it increases without bound. So, oh, and forgot to put this part. This goes towards positive infinity. So, that's the first half of this video. I didn't anticipate this going as long as it is, but I will make a second part of this so I can take a small break. Anyways, I will see you in the next one.